Okay, so in general, I give you a signal. Okay, I say, hey, please, expert, right? You're doing data science. Very good. I'm a physician. I don't know anything. Okay, please help us to do analysis. This is the data for you. Okay, please, I want the p-value less than 0.05. You understand p-value, right? You are such a good applied mathematician. P-value is important, right? 0.05, that's the mission. Okay, data for you. Go. Do the analysis. Okay, whatever. But this is kind of, well, not so dramatic, but sometimes you will encounter this kind of conversation. I ran into it several times. They say, hey, Hao-Ting, oh, you work on medical AI. Oh, you must be very good in deep learning, right? I said, well, what? Deep learning? Oh, yeah, okay. Okay, but anyways, I say, no matter you want to do what? Deep learning, fine, no problem. But are you sure there is a signal that you can analyze? Are you sure? You look at this. This part is oscillatory. That is what you are familiar with, like PPG. But what about this part? Are you sure there is a signal? If there is no signal, okay, no signal and contaminated by noise are two different notions. It is possible that you do not have anything over this period just because the lid it just fall down. You don't have any contact. The signal is totally garbage. Or another thing is you get the signal recorded, you are just you just do something nasty, so that signal has noise. Okay? No matter what, you need to distinguish all these parts so that you can get high quality data like this, so that you can do the analysis. And we have, in the very first lecture, focused on what is data analysis. And I said to study this kind of time series from my perspective, science is very important. We need to follow scientific thinking process. But what is scientific thinking process? Before you do some kind of science, you need to pay attention and take care of the data quality. I give you a signal. You need to check if there is an information. Is the information correct? Then you can ask how to quantify information. Usually, you get a bench database from online. People have done this part for you. But if you collect data yourself, you need to pay attention to this part. You need to pay attention to these parts. Okay, and if you may recall back in 2017, the Nobel Physics Prize was awarded to researchers who found gravity wave. Okay, I didn't have a gravity wave signal here, but I can guarantee you it looks like noise, just noise. Why noise? But how did they be so sure that there exists a gravity wave so that they can even do analysis? Actually, they have done several different things. They have to confirm it by several different recorders, see if there is really something in common, even do some signal consistency, statistical analysis, do some modeling from different or blind injection, okay, just from different angles to make sure the signal exists, so that when the signal really exists, they confirm there is signal inside, there is a gravity wave inside, then they can study the gravity wave. Okay, that is a very, very important part of this whole structure. Okay, and then now, a very basic question. How sure can you say there is a signal? How sure can you say so? Then there's uncertainty quantification, part of it. I will not say, oh, we answered the whole question, no. But I will give you one way to discuss this kind of signal. And the tool is based on the very recent developed bootstrapping algorithm to study the time frequency analysis. So let's consider a noise model, because in practice, noise is usually very nasty. You saw that. It is not always small, big, or whatever. It just changes from time to time, non-stationary, and whatever. So we need a more complicated noise model. so that we can guarantee, at least under this model, something good can happen. We can do something. That is what we want to achieve. Okay, thanks to Professor Zhou, I don't need to waste too much time explaining this model. Okay, this model is something you can say, wow, looks kind of crazy. You see, what is this symbol? Looks like infinite, right? And what? RD, what? Measurable, what is measurable? Who cares about that, right? Yeah, well, you don't need to care about that. No, you don't need. What you remember is, this is a noise model that is described by some mechanism, noise generation mechanism called G at time I. Okay, G at time I. You can view this as a filter. And remember what is filter, right? Filter, the lecture given by Professor Liu, you take historical data and you mix up the historical data and you get output, right? And you also know that, oh, if this is an LTI system, then you have to go to the Fourier domain, you have convolution, okay, all this kind of business. But here, don't make things that complicated, because that is not complicated enough. We need to make it further complicated that nobody knows what the hell is happening here. It's just some GI, some very crazy filter which can be very, very, very super nonlinear. And you take the historical data, some kind of natural injection of independent and identical distributed random variable. Just kind of noise, just input noise into it. And some kind of filtering machine which changes from time to time, just absorb the historical data and spit out some noise. And we just make an assumption that this Zi will have mean zero and finite moments. That's the only thing we need. Okay, so this is a model describing what noise is. The noise is something that we somehow give up modeling. Okay, we just say it is so complicated. We just need a very general condition that can be satisfied by most practical scenarios so that we can do analysis and get guarantee. We do not aim to study the structure of the filter. And if D is 1, it is called the non-stationary noise model. If D is greater than 1, it is high-dimensional noise model, which we may or may not encounter in this lecture depending on the time, because usually when noise is high-dimensional, when the data is high-dimensional and it's a time series, later on we will see something. The noise there can be modeled by this kind of high-dimensional thing. Okay, that is what I meant for the condition. The first one is we just need the signal, the noise, to have p moments. P is greater than 2. Oh, hold on. What is moment? What is p greater than 2? And this notation looks a bit crazy here, right? Don't worry. It just tells you that the noise is not as crazy as possible. The noise has a very well-controlled concentration property that it is not too big. It's not too big, and it doesn't go astray easily. It doesn't go astray easily. It will be kind of well-reframed in some domain, in some range, so that noise size is big, good enough. Okay, and the moment is a mathematical quantity language to say what's going on. And then this kind of dependence measure is the one similar to what Professor Zhou has introduced. What we try to say is, suppose I want to see how the system, this noise system at this moment, depend on the history. What we do is, under the assumption that we are injecting independent noises, I just replace the k step previous step. I replace it by an independent realization of noise, and to see how the noise at the current moment changes. Okay, if it changes very much, then it means the signal, the system depends a lot in the k previous step. But if it is just kind of well, not anything, like you don't see too much, then it doesn't have a very strong dependence. So this is the quantification, saying that you just try to quantify what the noise you have right now at time I, but you quantify and you replace the k's previous step by an independent input and see how different they are. Okay, and we want this guy to be as small as possible, as small as possible. Okay, meaning that the k's previous step doesn't really have any consequence at this moment. So this is a very convenient way to quantify dependence. And what we want is, as you can imagine, some kind of assumptions that, oh, this appears, the same condition appears in Professor Zhou's talk, saying that, okay, the k step, it will have some kind of good decay, okay? It doesn't depend on the historical data too much. And everything I will talk about from now on, you can always assume that P is sufficiently big and this chi is sufficiently big, meaning that the noise is well controlled, it's not crazy, okay? And its dependence, it may depend on infinite previous steps, but dependence is very weak. It may depend on some historical data. So the noise has dependence, we have quantified it. The noise doesn't need to be Gaussian. It can have some kind of crazy behavior, but it is well controlled. So that is kind of, at least in practice, good enough and general enough model to quantify most of the noises we encounter. So we want to ask, suppose this is our noise, then what can we say about, for example, the time frequency representation I showed you, how certain you get some components or some signal there. Okay, so that will be the model of noise. Yes?
So if you want to propose that the noise is independent of the previous, we will find to quantify the E hat. Is that true?
What do you mean?
Because like you said that suppose that like the noise is not is really weak, the weak depends on the past, right? So how to prove that? How can I prove that? And can we prove that by?
This is an assumption, not proof. You don't need to prove it. This is the model assumption. You just say, right now, we have this kind of mechanism, noise generation mechanism. Yeah. And this noise generation mechanism tells you that the noise right now does not depend on previous steps. You can make this assumption. Yeah. You can just like you say, I will say, okay, no matter what you say, all the noise are independent. You can make this assumption. But this assumption is too strong. It is not realistic.
So can we test it experimentally by quantifying the E hat?
This is very challenging. Okay. This is very, very challenging. For example, I give you a noise, okay? Your question becomes, what is the dependent structure of this noise? What is the dependent structure of this noise? How to determine it? This is itself a very, very challenging statistical problem to my knowledge. Even if you say the data, the noise is generated by some stationary random process, it's stationary, totally stationary, then how to confirm that it is really stationary? I mean, even this question is very, very challenging to achieve. Not to mention, right now it's totally non-stationary. We do not ask for anything stationary. We only ask that the moments are well controlled. It does not have long dependence. That's the only thing we request. Then how to generate statistics to make sure that such assumption is satisfied by that noise? I don't know. It's a very challenging problem. Yes?
I had some question talking to you about gravity wave. So, for example, if we have some signal from our body, we usually know what it is about. So if we want to find out some new signals, is it more important to take away those signals that we know already and analyzing the noise?
Mm-hmm.
I think it's more important to analyzing the noise, but I think we are key learning about just removing the noise and learning about the main signal. So yeah.
Okay, so what you are asking is, will there be any structure inside the noise? Will there be any structure inside noise? And you suspect yes, right? Otherwise, you will not ask so.
Yeah.
It depends on the question. So for example, we haven't discussed how to study the brain wave. If you look at the brain wave, usually the brain wave itself looks like noise. It is usually modeled by a random process. And for that random process, it does have structure. And we do need to quantify it. Okay, and how to quantify it, that hasn't been covered. Okay, but that can be quantified. What we are saying right now is, suppose inside the ECG, the brainwave signal, there are some structure. For example, I showed you the spindle structure. You model the spindle structure as an oscillatory signal. Then how to analyze it? That's what we are talking about. After we get the spindle signal analyzed, you can ask, suppose you remove the spindle. The remaining signal still looks like just like noise, like a stationary noise, like a random process. Then how to study it? Okay, that's what you're asking, right? And that we may cover it a bit in the end, but not too much, because that becomes a study of a random process. And for non-stationary random process, how to study the random process itself usually is already very challenging. So later on, in a few slides, you will see there will be an alternative to model that kind of non-stationarity, but you need a very, very strong assumption. You need a very, very strong assumption that I will introduce in a bit, so that in that setup, you have several different ways to quantify the non-stationarity. Okay? And that quantify non-stationarity can be an alternative, can be the feature for whatever analysis you want in the future, in the next step. Okay? Good. Any more question? I hope so far is not too technical. Okay, good. I still have 15 minutes, as I promised. So just bear with me, and it shouldn't be too bad. Okay, first, I want to tell you a bit story about Gaussianarity of short-time Fourier transform, because this is kind of a very starting point of analyzing signals like algorithms like synchrosqueezing, or if you like to study random processes using time frequency analysis, like you asked, then you may need to understand what will be the structure or the behavior of short-time Fourier transform. So you remember, this is short-time Fourier transform, and you can discretize it. And you know everything. Its discretization looks like that guy. You have the window, you have the signal, and you evaluate the Fourier transform centered at time t-LO, and you evaluate short-time Fourier transform. So you can easily see that, hey, look, if the signal z is Gaussian, it's a Gaussian random process as an input, then what do you get? Gaussian, right? The Gaussian has a very strong property. Even if that is dependent, you sum them together, you still get Gaussian. Not a problem. Everything's Gaussian. Perfect. We are happy. But the input signal usually cannot be Gaussian. In particular, noise and everything rarely be Gaussian. Okay, not even independent. Although, if you go to engineering environment, sometimes they are happy about IID Gaussian, which is good enough, and there is a reason for that, because what I will show you later, that is actually most of the things are Gaussian in the time frequency domain. In general, you can say, hey, now Z is not Gaussian. If Z is not Gaussian, you still have the same formula, isn't it? And what do you see here? you sum n components divided by square root of n. For students who ever learned some probability, this may ring the bell, right? Some kind of something called central limit theory might appear, isn't it? So it tells you that suppose you fix TLO and fix eta k, you fix both of them, you just focus on the randomness of zj, then you can actually easily show using some short range dependence, M dependence trick, that by central limit theory, this guy is Gaussian for a given pair of TLO eta k. Just one pair. You can easily show it. But there's a but. What we want is this guy, and hopefully this guy is Gaussian for any pair of TLO and eta k. Then you can start to imagine the magnitude of the difficulty. Because there will be a lot of dependence. There will be a lot of dependence in all the construction. And you can say, hey, look, for one pair, you get something very close to Gaussian. When you say very close, what do you mean by very close? You may say, hey, look, I learned Airy Bayesian, right? We may quantify how far the distribution is to Gaussian. We get some quantification, but don't forget, we have n square entries, pairs that we need to compare. You cannot achieve all of them. That's the problem. You can only get maybe finite numbers. But even finite numbers, that is challenging enough. Challenging enough. Okay, so, but numerically, it tells us that it is always Gaussian. What I'm showing here is when the input signal, the noise, pure noise, is time-varying AR with student T4, which is a fat-tail and time-varying autoregressive model. That is non-stationary. In this case, all these axes, 105, 230, 355, they're so small that you cannot read. Those are the time. I randomly sample different time and the different frequency. And each block means that I realize the short-time Fourier transform at that time and the frequency for 1,000 or 10,000 times, I forget. And then I compare it with the Gaussian distribution. And this is a QQ plot. So you see, for every almost all time frequency pair, the QQ plot are just flat, diagonal, which means they are very, very close to Gaussian everywhere, even if the input data is non-stationary. Okay, so that is what you can say, you can see from simulation that you would expect the short-time Fourier transform to be close to Gaussian. You have Gaussianarity of short-time Fourier transform. And in general, if you ever learned some random field theory, then what we are trying to do is we want to prove that the random field you construct over the time frequency domain is actually close to Gaussian. That's what we want. Okay, so the result is actually true. We can prove that, yes, it is really Gaussian, very close to Gaussian. Not Gaussian, but close to Gaussian. So we need some assumptions. First, the signal, the noise, is non-stationary, like I mentioned just now, but we assume that you have some conditions. There are technical conditions you can ignore. Just tells you that it is short range dependence, and you have finite high moments. And now, let's consider the following thing. We consider the different frequencies that we have interest, eta 1 to eta d. Just the different frequencies we want to study. And now we consider all possible short-time Fourier transform with window h and with window derivative of h. If you remember, we want to study synchrosqueezing transform, and in synchrosqueezing transform, we have to take differentiation of the short-time Fourier transform to generate the reassignment. So we need to study the Gaussianarity of all those pairs. So you see, we now consider 2D complex vector. And this vector, because epsilon is a non-Gaussian random noise, VL, this vector, is actually also a random vector. It's a random vector. And we assume that D, we allow it to grow to infinite. Meaning that when you have more and more points, the signal is longer and longer, we allow to explore more and more frequency axis, frequency entries. Okay, that's the condition. Then what we can show is this result, which looks a bit complicated, but let's take a look. So this says that we can construct a Gaussian process, epsilon hat. Okay, that is, we can construct precisely this one Gaussian random process that has exactly the same covariance structure of the input non-stationary noise. Okay, and you can construct the same vector VL, V hat. And now we can compare the V hat difference, L2 non sense, and the max over all time. Okay, this is the max expectation, and you can view this as kind of Dudley or maximal value theorem, extreme value theorem from random process perspective. This guy actually can be controlled by something on the right-hand side, which looks very complicated. But don't worry, let me show you. It's actually very simple. So first, C prime is just a constant that depends on the window and the moments condition and dependent structure of the data. And all this is SI, 1 over P, PS, okay, what the frick, so crazy. But don't worry, it is crazy, I know, but just forget about this craziness. Just assume, view this as 0. We just care about when P is big and the chi is big, meaning that the data is very good. It has many, many moments, okay, and the dependence is short. In this setup, 1 over S is just 0, 1 over P is 0, 1 over everything is 0. You just get D 3 quarter and N 1 quarter, and you have this and that. And now, what is this guy? What is M? M is actually the length of the window you consider. Okay, and if we choose M to be of the order n squared, then this term disappears. The meaning of this quantity is a bit more delicate. It is related to the noise size, how the noise is carried over Fourier domain, and so on. I will not talk in detail, but this just tells you that for the ordinary window length we choose, it gives us a good, sufficiently good, high-quality approximation of Gaussianarity of the short-time Fourier transform. So the summary is when P and chi are big, then you get this quantity. Okay, that is, you can actually get n raised to power 1 cubic, that many frequency entries that are Gaussian. But although this is one result, I was happy to write a paper, but it is still not optimal. Okay, we are still trying to do some exploration, but using the technique, we know right now we cannot bypass it. But numerically, actually, if you remember, we have n points, n data points, then we can quantify n frequencies, or even dense frequencies like n raised to power 3/2. Okay, that many frequencies. Numerically, you can say that almost all of them are Gaussian. So at least I will hope D to be n raised to power 1 minus epsilon, or even n raised to power 1.5 minus epsilon. That should be all true. But right now, I don't know how to prove it. And I'm talking to probabilists, and hopefully someday I can show, maybe 10 years later. Yep. So anyways, this tells you that we have Gaussianarity, but it is already 4:10. I have 5 minutes, and I also want to give you some hands-on. And which to keep my words, it is obviously that I cannot achieve it. But so I will do the bootstrap in next lecture. But I want to tell you one thing very quickly, how to achieve this kind of bootstrap stuff and how to get the uncertainty quantification so that in practice you can answer some questions. Okay, recall, I give you the signal. The black one is the clean signal. The gray one is a noisy signal. On the right-hand side, you get this guy. So you can answer me, what do you see? Do you think there is a curve here? Isn't this too crazy to say there is a curve? But there is really a curve here, trust me. Okay, because this is the signal I generate. But just the noise and some structures that is masked. How to quantify its existence? There are two potential ways we can do. First one is you denoise the time frequency representation, for example, using concept, which we haven't discussed. Yeah, and the other one is to do bootstrap, and that is the way I will tell you today. And the concept will be later. And with concept, actually you can blend in the learning procedure to study, to learn what is kind of the ideal threshold. Okay, there were several things that can be achieved. Okay, so I will skip this part for now. Basic idea is this one. I will explain all details later, but what we do is first we will model the noise by locally stationary, and I will explain to you what locally stationary is next time. Then you approximate locally stationary random process by a time-varying autoregressive process of some order B that you can choose. Suppose you can get a good approximation of the local stationary random process using time-varying autoregressive, then you can generate bootstrapped noise. For example, generate some noises. And you generate many, many copies. And you recall the notion called bootstrap, don't you? The bootstrap gives you an opportunity to sample, to reconstruct the distribution of what you have interest. So what you do is, from this bootstrap noise, you apply synchrosqueezing transform, and you obtain the synchrosqueezing transform for the jth time. And you have m times, and all of them are independent. So depending on how accurate you can approximate local stationary random process, how well you can approximate it, then you can show that how accurate you can approximate the distribution of this random process. Okay, and I will tell you details next time about how to do the fitting and blah, 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 and the theory, okay? Okay, so this is a result, okay? This is one realization from the model, and this is a bootstrap noise. For this noise, is a very typical locally stationary. You can see that it's big here, becomes smaller, right? Becomes smaller and become large again, large again. This is a very benign non-stationarity, okay? And this is a bootstrap one, which is not bad. And in this case, you can actually achieve very good approximation of the random process, of the distribution. And here, the x-axis will be 1,000 or 10,000 realization of the same noise, which is the ground truth model. The y-axis is by bootstrap. So you can see that the bootstrap gives you a very nice approximation of the true distribution. Okay.